7, question 30 on the photoelectric effect. So you've got a metal plate that emits electrons when a certain wavelength of electromagnetic radiation is shone upon it. So you're going to get electrons ejected here. That's going to cause a current flow that you can see or read off on this ammeter. When light of wavelength 605 nanometers is incident on the metal plate, electrons are released with zero kinetic energy. So what that basically means is that your wavelength of 605 nanometers corresponds to a frequency that is going to give you your minimum amount of energy required to eject the electron. In other words, the work function. So show that the work function of this metal is 3.29 times 10 to the negative 19 is your first question. So the first thing you need to do, you've got a wavelength given here, 605 nanometers. You can use that to calculate frequency. Because remember, the work function and the energy of the photon, which is really saying the same thing here, is proportional to the frequency. So you need to know what that missing frequency is. So frequency is V divided by lambda. So 3 times 10 to the power 8, because all electromagnetic radiation travels at that rate. Your wavelength is 605 nanometers. Nanometers is times 10 to the negative 9. You'll get a frequency value of 4.96 times 10 to the 14. So that's just half of your marks here. In fact, only really half a mark for doing that calculation. You now need to figure out what the work function is. So you've got to prove that this value is the work function. So the work function for this will be h times f naught, which is the threshold frequency. So if this is being ejected with zero kinetic energy, it means it's just enough to eject the electron and no more, which means it's right on the threshold frequency. That threshold frequency is what you've just calculated here. Planck's constant is something that you can get from the data sheet at the front of any past paper. So it's 6.63 times 10 to the negative 34 multiplied by this value of frequency that you've just calculated. A wee bit different from some examples because it doesn't give you the frequency, it gives you the wavelength instead. So your energy will come out as being 3.229 times 10 to the negative 19 joules. So that proves that there. All you've got to do is calculate out the frequency that corresponds to this wavelength and then plug it into E equals HF. B, the wavelength of the incident radiation is now altered. Photons of energy 5.12 times 10 to the negative 19 joules are incident on the metal plate. Calculate the maximum kinetic energy of the electrons as they leave the metal plate. So the value of energy from here to here has been increased. So if you've got a larger value of energy, that means that the photon is going to have more energy itself. This is the amount of energy required just to bring the electron to the surface and no more, so just to bring it to here. But if you add more energy onto that, then that energy is going to be used to propel that electron a wee bit further. It's going to give it a certain amount of associated kinetic energy. So what you're really calculating here is the difference between this energy and the work function. So the kinetic energy that it has is going to be the energy of the photon minus the work function. So the energy that the photon has in this case is 5.12 times 10 to the negative 19. The energy that it gives up, the minimum amount of energy required to eject an electron to the surface, is the work function. And anything that's left over can be used to propel the electron away from the surface. So it's used as kinetic energy. So that's 1.83 times 10 to the negative 19 joules. Second part, a wee bit trickier. The radiance of this radiation on the metal plate is now decreased, so the amount of radiation falling per unit area has gone down. So it basically means that the source of the electromagnetic radiation has been moved further away. State the effect this has on the ammeter reading and justify your answer. Well, current decreases. That's the first thing. You're going to get 1 mark for that. Your remaining 1 mark is going to be for explaining why that is. So the current is decreased, and the reason for that is because there are less photons falling on this surface. So if irradiance is decreased, then it means there's less radiation falling per unit area. So therefore there are less photons. If there are less photons, then there are going to be less electrons ejected. Less electrons flowing across here means less electrical current. So current decreases because you've got less photons, and less photons mean less electrons. Because it's these photons of electromagnetic radiation, one of them will eject 1 electron. So if you reduce the amount of photons that there are, then you reduce the amount of electrons that you produce as a result. So the current goes down. So 1 mark for this, and really half a mark for saying less photons, and then half a mark for saying less photons will produce less electrons, because what you're really looking at is 1 photon being equal to 1 photoelectron, which is just a fancy word for the electrons that have been ejected.